right, so we'll go ahead and get started at least with one projector here. Sorry for the delay. From last time, we were looking at building this database, designing and implementing this database to support that account system that we were looking at with annuities and savings accounts. And we started out by creating a person table and an email table that was a result of a sketch that looks something like this. And then we started thinking about, well, how do we do the rest of this? How do we model an annuity? How do we model a savings account? And how do we handle this one extension where we allow an account to be owned by multiple people? So this one savings account can have a husband and a wife on it, or a child and a parent on it, or something like that. And that or the annuity has multiple people on it, an entire family on the annuity or something. And then, of course, one person can still own multiple accounts. We're probably going to want some sort of a many-to-many relationship there. So let's take a look at the UML diagram here and think about this. Well, if I just gone with a straight-up copy of this UML diagram, where we've got an account, an annuity, and a savings account, I might come up with a sketch that looks something like this, where I've got a table for annuities, and then another table over here for savings. I'll just abbreviate it there, and annuity. I'll abbreviate it there. That is an inheritance model, an inheritance model, an object-oriented programming model, right? Edgar Codd in 1970 was not thinking about inheritance because inheritance hadn't been invented or developed with object-oriented programming yet. The relational model is a completely fundamentally different model of modeling data. So we could do something like this, where we've got, say, the common functionality of, say, the account number here, the owner, et cetera, et cetera. That's going to be in this table up here that represents all types of accounts. Right? And then we'll have yet another table here to represent annuities and another table to represent savings. Right? And maybe there's some sort of a many-to-many relationship there. Right? This is a perfectly fine strategy for resolving these two fundamentally different models, an object-oriented programming model and a relational database model. This is called a table per class strategy. Right? I don't want to do that because it's a lot of tables. Right? With this simple model, we've got 3 tables already, right? One for every single class. If you've got a much larger system with dozens and dozens of different classes that are modeled in the database and inherited, then you've got dozens and dozens of tables. Not only that, but every time that you pull data out for one account, you are necessarily joining to another account. If you've got an inheritance hierarchy that is like 4 levels deep, you're going to be doing join, join, join all the way over. Right? Lots of complicated stuff. So let's go ahead and simplify it. And let's suppose that we have instead 2 tables here, one for savings and one for annuities. Right? Now, there is still this account idea up here, but it's not actually going to be a table, right? Instead, these are kind of shadow, oops, not all the way there. These are kind of shadow relationships here, right? And then we've got an annuity and an account, right? This is a table per subclass strategy. And that's also yet another perfectly fine strategy to follow. Again, the problem is every time you want to pull somebody's accounts, you need to, like there's a person over here, right? And they're connected to all these savings accounts over here, all these annuity accounts over here, right? Again, it's a table per subclass. That only relieves me of the need of eliminating one class here. I want to go all the way, right? I want to have one class that represents any and all accounts, right? So let's call it account. There we go. Now what this is going to do is this is going to represent all possible accounts. It's going to have the common data that is common to every single account, but also it's going to have monthly payment and term years, which is relevant to an annuity, and some records that's going to be null. Other records it's going to be specified because it's an annuity class. And other records will have balance and annual percentage rate, right? And that data will be in there and missing for annuity accounts, but it'll be there for savings accounts, okay? So let's go ahead and start designing this. First of all, what's the very first thing that I should do? Primary key, not null, right? That's always the first thing that you do with any table, right? That gets you second normal form for free. Account ID, and that's primary key, int, not null, et cetera, et cetera, et cetera, okay? All right, well, what else belongs in an account? An account number? Did we do the account number already and talk about surrogate and natural keys? Does that ring a bell? If not, okay, let's retread. An account number. Let's come over here and take a look at the account number. Is the account number an integer? Not the way that I've represented it. I want to be allowed to put in hyphens and A through Z's or something like that. And so here it will be a varchar. Now you might be asking yourself, why do we have two things that uniquely identify an account here? An account ID and an account number. Why don't I just go ahead and combine those and just use the account number and be done with it? Well, first of all, it's a varchar. And as we've already seen, case sensitivity issues, I can't hand in my project because I used a lowercase p instead of an uppercase p, right? These things matter, right? So don't have those headaches with respect to these, with respect to strings, right? Is it ASCII? Is it Unicode? Is it case sensitive? Is it case insensitive, right? Get rid of those headaches. That's not your key, right? We'll keep both of these. One of them is going to be what's called a surrogate key. And the other one is going to be what's called a natural key. So a natural key example would be, how do we identify a person in the United States? Social Security number. Right? How do we identify a person here at the at UNL or out in the any of the NU system? NUID. Right? Those are called natural keys because that's a natural way to go, right? Lexicographic order is natural order. Ascending order for numbers, that's natural order. Think though, right? Are we responsible for maintaining these things? No, we don't control them. Somebody else controls them. The Social Security Office controls that one. Some goon over in Canfield controls these or something, right? I don't know. I don't know who does it, right? But in any case, do you think in the history of the Social Security Office or in the history of UNL, nobody has ever screwed up and accidentally assigned the same NUID to two different people or to the same person, one NUID? Nope. So we will not let these natural keys dictate to us the integrity of our database. If we have no control over them, they should not be controlling us. We're going to use a surrogate key, an automatically generated primary key that will identify uniquely identify an account. Right? We'll keep this, and we'll also need to make sure that it's unique. And that it's also a key, but not the primary key, a secondary key, although we don't call them secondary keys. Okay? So we will need to make sure that this is unique. We will need to keep track of it. Because imagine if somebody calls us up and says, oh, we screwed up. That Social Security number is wrong. If we use that as our primary key and our foreign key over here to this table and another table and another table and another table and another table, and by the time we're done, we've got a dozen tables that refer to this one invalid wrong value that they screwed up on, right? That means that when they inform us that we need to fix it, that means fixing every record in every table in our entire database. Whereas if I had used a natural key instead, or a surrogate key, and then just kept track of the natural key, Social Security Office comes and talks to us and says, okay, that Social Security number is wrong, please update it. Okay, I update one record in one column in one table, right? Much, much better strategy than having it dictate my entire data integrity in my database. If you do not control it, it should not control you. Don't do that as your primary keys. All right, what else do we need in this table? We need a monthly payment in term years. We need a balance and an APR. So monthly payment, and this is going to be a double. There is no currency. You can go ahead and use like a decimal and then you have like 10 digits of accuracy and 2 decimals of accuracy. You can use syntax that looks like this, right? Why? Eventually, when you pull it out, you're going to be marshalling this and storing this in a Java double. That better match, right? And you better not lose precision when it comes out. Don't use a float. A float is just an inferior double, right? With only 7 digits of accuracy. Right? There's my monthly payment, years or term years. There's my, that's an integer. Yep. Now for annuities, these are going to be specified and they're not going to be null. But what about savings accounts that have balances and an APR? And both of these are doubles. Double and double. Are these two relevant for an annuity? No. Are these two relevant for a savings account? No. So probably I'm going to allow these to be null. Nullable. Right? So that for one type of annuity, these will be missing data. Right? Don't use flag values like 0 or 0 because you can't distinguish between a flag value and a savings account that truly has nothing in it. Right? If your savings account has a 0 balance versus, well, no, this is actually an annuity account, how do you tell the difference? Don't tell the difference. Allow them to be null. That does ask a good question here, though. How do we determine the difference between an annuity and a savings account? What else could I put into this table to help me out? A what? Like a type, right? Which is a varchar. And it could be a single character A or a single character S. Or the word annuity and the word savings. Right? Gee, that sounds familiar. Where have we done this before? On your class? Well, hopefully not on your classes. Your classes are themselves the type. But from the CSV files, when you pull items out of a CSV file, how do you know what type of item it is? E. Equipment, P for product, and S for services, right? That's called a discriminator column. Discriminator column. And it is the workaround between the two models, the relational model and the inheritance and the object-oriented programming model. How do you reconcile these two? This is the strategy. Have one table to simulate them all, and have this discriminator column telling you that this record in this table is this type right here. Okay? We're going to implement this here in a second. Before we do that, let's go ahead and model the person and the account. How do you model the fact that this person owns this that this person over here owns this account over here? So I'll go ahead and draw these as, you know, truncated tables here. There we go. So how do I bring those together? A what? A foreign key? Not just one foreign key, but 2 foreign keys. How did I bring a game and a platform together? And what kind of relationship is there? One game can be on multiple platforms. One platform hopefully has multiple games. That is a many-to-many relationship. How did we end up doing that? With a table in between with 2 foreign keys. Let's do that here. Right? Any options for the name of this table? What should we call it? We could call it person account, I guess. Account person. Which one goes first? What did we do that, or did we take that strategy over here though? We didn't call this game platform or platform game to join them together. What was it modeling? That game is available on that platform. What was the verb there? Is available, right? So what about here? This person blanks this account over here. This account is blanked by that person over there. Like access? Like Like this person accesses, like that, this account. Yeah, that could be one verb. What do we call it over here in our Pojos, our plain old Java objects? What did I call it there? It's the owner, right? So owns, you could put that, owns, right? But generally, you like to name things nouns or adverbs, or adverbs. Nah, not adjectives. Adjectives would be like interfaces. Ownable, right? Adverbs would be like owns it well. That doesn't make any sense either. So what is the noun form of owns? How would you call it? Owned by or ownership. I like that. Right? Owned by would also be perfectly fine. Although from the other perspective, this account is owned by that person, but is this person owned by that account? Right? There's a two-way relationship here. And if you keep it as general as possible, then it makes sense both ways. Ownership. This person's ownership of this account's ownership is that person. Okay? What's the first thing I should do in this table? The first thing that I've done in every table is primary key, integer, not null, named after the table, ownership ID. Now, how do I bring these two tables together over here in the game database? There's a game ID, there's the foreign key, there's the platform ID, there's the foreign key down here. Remember, now I've got two parents. This is two-parent, one-child relationship here. Right? And so the foreign keys always belong in the child table, just like over here. Right? So person ID, and I'll just make a note here that refers back to the person, and then account ID, and I'll make a note that refers back to the account. Right? Anything else that we would want to put in here? Well, I kept it simple. But what did we do over here? This is called a join table, but it's not a pure join table because it has some additional information here, like publish year. Right? If publish year appeared up here in the game, then that means that game was published on every single platform in the same year, and we know that that's not true. There are plenty of exclusive titles out there that you have to wait a year for or something. If we'd put it up here in the platform table, that means that every game on that platform was published in that year. Right? That seems wrong too. The publish year is a function of both the game and the platform. If there were something else, like say account open date, right? This person opened this account on that particular date. But since we're not modeling that, I'll just go ahead and cross that out. Right? But if there was something that were a function of both of those two things, you would put it in the join table. Okay? There, along with the diagrams that we made last time, along with this one, that's exactly what we're expecting on your next design document after the Friday after the break. We're wanting to see, clean it up a bit and maybe have better handwriting than I did, but we want to see what you're planning. How many tables are you going to have? What's in each table? What kind of inheritance strategy are you going to be using, right? Do you have a one-to-one relationship there, a one-to-many relationship, a many-to-many relationship? That's what we're wanting to see. There's these kind of sketches, okay? Now, for the remainder of our time, let's take these two sketches and bring them together to continue our database development here. Right? I'm already using my database, so let's go ahead and bring these back in, the email person, the table person. The first thing I'm going to want to do is probably take care of this account table now. Right? So let's do that. Create table if not exists, account. Right? Again, what's the first thing I should do? That primary key named after the table, integer, primary key, not null, auto increment, let the database do its job. What else do we want in there? What did I put in my sketch here? An account number. Right? Account number. Right? And we already know that that's going to be a varchar because that's the business rules, right? 255. Again, why am I doing 255? It's just historic reasons. Right? Now, if you had a business rule in this accounting system that an account ID was at most 25 characters or always 25 characters, then you would put that in there. Right? We don't have that information. I didn't bother to think about it, so I'm just going to go ahead and put 255 in there. In real life, you'd go back to the stakeholders and say, what is this, right? Give me an example of an account number, or give me all of your data so I can look through it and see that, well, some of them are 10 and some of them are 15, but the maximum seems to be about 25. So we'll go ahead and go with that, right? Trust but verify. Never listen to the business side, or trust them that they know what they're talking about, but then go back and verify that they do know what they're talking about, right? All right, should I allow that to be null? Because that's what it is right now by default. Probably not. That would be extremely bad data. If you had an account with no account number, right? The auditors would be, their eyes would be bleeding at that, right? No, we're not gonna allow that to be null. Should we define a sensible default though? Probably not, right? If you don't have an account number, then we should generate one and put it on there. You shouldn't just be inserting this data willy-nilly, right? What else? We want to make sure that that's unique, remember? We'll come back to that. Now we want that discriminator column, that type. So type, varchar. This could be a big giant string, or it could be a single letter if you wanted it to be, right? In any case, we're not going to allow this to be null because it has to be an annuity account or it has to be a savings account. There's no other option here, right? There's no mysterious abstract class up above, right? Because we made our super class into an abstract class. If it's missing, then it's bad data, okay? Do we want to go with 1 or do we want to go with the full name? I'll just go ahead and go with 1 for now. The reason that you would not want to go with 1 is because maybe you've got multiple, like you've got 2 things that begin with S, and so now you need to disambiguate those, and you need more room, right? Yagni for now. You ain't gonna need it for now. What else do we have? Monthly payment, which is a double, right? Should I enforce that it's not null? Probably not, because is a monthly payment going to be relevant to, say, S is equal to savings and A is equal to annuity? Is a monthly payment going to be relevant to a savings account? Nope. So we'll go ahead and let that be null. The other one was term years, integer. That's also going to be allowed to be null because it's irrelevant for a savings account. And then balance, double, and APR, double, allowed to be null for the exact same reasons that I just mentioned. That takes care of pretty much everything in here except for that star that I have. I want to make sure that this account number is unique. So I'm going to come back up here and I'm going to add just one very simple keyword here. Actually 2. Unique key. There. That's it. The database will take care of it for me. You can never have 2 account numbers that are 1234A and 1234A. That's bad data, and the database will reject that. I will never be able to rename the account number from one thing to another thing if that account number has already been taken. The database would reject that. Right? That's a uniqueness constraint. Okay? I'm saying that this column has to have unique values. You can do it without a key. Okay? But that's a bad thing to do too, because eventually you're going to be querying this database. And if you're querying this database, if it's in order, as we've already seen many times before, if something is in order, you can exploit that ordering. If something is sorted, how can you exploit that? To search through it. What kind of a search can you use? Binary search. That's what you had to do on your first assignment. And if you didn't, then it would take weeks to execute, literally weeks to execute, right? So I'm going to go ahead and put a key on this. A key is also called an index. An index simply means that that internally the database is managing a secondary list that is sorted with respect to the account number. It does that automatically with primary keys, by the way. It will sort all the account IDs, and so if you're searching for a particular account ID, it can exploit something like binary search to immediately, almost immediately jump to it, right? Without this, and you've got, say, 1 billion records in the table, right? If you did not have this key here, and you had 1 billion records and you were searching for that one account with ID 1234A, guess what? You're starting at the beginning. That's not it, 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 etc. Right? You're doing 1 billion operations if you've got 1 billion accounts. Right? And that is going to take a non-trivial amount of time to locate. Right? In the case of your first assignment, right? If you did it naively like that, then it would take literally weeks to do that. And in case you think that this is not that important, it is. Right? There's no less than 3 times in my career that I've seen databases that were horribly, horribly designed, and they were just resigned to the fact that this report took 24 hours to run. The second you put a key on it, magically it becomes 2 seconds. Right? Oh my God, you're a god. How did you do that? I'm a computer scientist. I know what I'm doing. Right? That should be your answer too going forward. Right? And whoever wrote that query clearly did not know what they were doing. See that all the time. When I was a grad student, there was another grad student from physics came over, and he was just wandering the halls until he found somebody that would actually help him. And he says he had some C++ program, and he said, I've been working on this for weeks and it doesn't work. All right, well, I don't know any physics, but show it to me. And basically, he had created, so those of you coming from a C background will immediately appreciate this. They were working on large data, right? And so he had a bunch of, say, doubles, right? Double data, right? And he knew that he had a lot of data. So he created this, this array with, say, 100 million data points here. Those of you coming from a C background, is that going to work? It's going to be immediately Stack Overflow segfault. Why? You can't allocate that much data on a stack. All I did was change that one line of code to be data is equal to, and it was C++, and I don't remember how to do it now. Something like this. Well, it was a double. Right? There. Something like that. Right? And immediately all of this stuff started working. And he sunk down into his chair and said, it's taken me weeks to figure this out. What did you do? Why is this? Well, you don't know the difference between the stack and the heap, right? That's something that you would know from computer science 1 or 2, right? And so, yes, you wasted I'm sorry that you wasted 7 weeks of your life, but that kind of knowledge, that small amount of knowledge, turns out that it's like so valuable in the real world, right? So make sure that you're taking advantage of everything that we try to teach you, right? If you ever have a database and you're searching along that column, put a key on it, put an index on it. Index key, they're aliases of each other, right? Without that key, your queries now take 24 hours to run, if they run at all, right? With that key, now they take a matter of instantaneous or seconds, right? Okay. Good. There's my table so far. Now I need to bring them together by putting in this join table here. That's simple enough. Create table if not exists. Ownership, I think is what we called it? Ownership. Copy paste. Oops. Copy paste correctly. Right. Don't do that in general. Ownership. But it's a primary key, not null, auto increment, ... Right? I also need a person ID, right? Int, not null. And I also need a, what else? An account ID, int, not null. Right? Account ID, int, not null. Right? There we go. And the table. Now, these are not foreign keys yet. Remember how we did a foreign key for the email table over here? We said foreign key person ID references the person table. We'll likewise do that here. This person, the owner of the account, references the person ID. Now, if you had, like, say, multiple people on here, you couldn't use that same column name over and over again. That person and that person, like that person owns the account, but that person manages the account, or that person is my broker or something like that. Then you would have to be more specific. The owner ID references the person table and the person ID within the person table. That's another way of doing it. I'll go ahead and keep it as person ID because we don't have that issue here. But where might you have that issue? Your project, right? Keep that in mind. All right, so there's my foreign key, references a person. I also need a foreign key. The account ID references the account table and the account ID within that table. Before we bring this all together and conclude on it, I also want to bring to your attention some data integrity here. All right? So suppose that we have a person, Joe, over here, and they've got an account, a savings account. Joe, person 123, and they own account ABC. Should I have two records in my database where I've got 123 ABC, 123 ABC? Can you own an account twice? Like, I really own this account. I really own this account 3 times, 4 times, 5 times. Does that sound like good data to you? Probably not. These two things right here, I want to make the combination of them unique. Let me use this right here. I want to make sure that the combo is unique. That if I have 1, 2, 3, and then ABC as values here, you will never have 1, 2, 3, ABC duplicated. This same person can own a different account, DEF. That's perfectly fine because that's what we want. One person owns several accounts. This one account, ABC, could be owned by 987, right? ABC. That's perfectly fine too. What I want to do is I want to make sure that this combination, this A-B combination, that combination is unique. And I can do that by putting in what's called a check constraint, or a uniqueness constraint. So constraint, unique pair, right? Unique, and then I'm going to put in the combination of the person ID and the account ID. Oops, account ID, there we go. So this is a constraint on the database. For example, uniqueness. That's actually a constraint as well. And this is a uniqueness constraint as well. It's just a different way of doing it. I want a constraint, and I'm naming my constraint, unique pair. Note here that these are backticks. This is not a single quote. And I'm saying that the unique combination of these two columns has to be, or the combination of these two columns has to be unique. I would never be able to insert data that looked like that, right? Where 1, 2, 3, ABC, 1, 2, 3, ABC. And you know, otherwise, if I didn't have this constraint on there, I could have somebody owning an account 5 times, and that doesn't make any sense. Okay. Another type of constraint that you can add to all this is what's called a check constraint. I'll do it up here, not on this one, but on this one. So remember that APR is going to be on the scale of 0 to 1, right? So 0 to 1. You can kind of enforce that using a check constraint. Check, APR is valid, right? Constraint check, sorry. Check. And here you can put in any logical statement that you want. That the APR is at least 0 and APR is at most 1. I suppose you could technically have an APR that's greater than 1. Wow, that's a great savings account, right? It's paying you 200% interest annually, right? Definitely take all of your money and everybody else's money that you can find and put it in that account, right? Because that's awesome. But otherwise, you can put in this check constraint. Spoiler alert, the check constraints are not actually enforced in MariaDB for MySQL compatibility reasons. But you are welcome to go ahead and write them. It will accept them and it'll run them. It just won't enforce them. So let's come back up here and make sure that we're dropping stuff to make sure that this actually works. Drop table if exists. I need to drop the ownership table before I drop the account table because it refers to both of those. In fact, I need to do that before the person. Right? Drop table if exists. Ownership, person, and account. There we go. And now let's run this entire script to make sure it's all good. Green as far as I can see. Now in our last 8 minutes here before you head out to spring break. My scribbles here don't look great, but they're okay for a draft. That's why we draft, right? I want something that looks nice and pretty like this. Do you think that I put a lot of effort into making this? Just like this UML diagram? No, I just installed something and let it do it for me. Same thing with MySQL Workbench. I'm going to create a new model. Right? Actually, before I do that, I need to save this. Sorry. So let's save this as, save as, foo, okay, it is. It's saved as foo.sql on my desktop here. I'm going to go ahead and come up here and go import, where is it? Where's import? Import, reverse and engineer a MySQL script. Let me select that SQL script that I just developed. Foo, there we go. And hey, that looks nice. There's a checkbox here. You can't see it very well, but it says, place imported objects on a diagram, an ER diagram, an entity relation diagram. Execute that for me, please. Continue. Close. Ooh, that almost looks nice. Let me move that around. There's account. There's ownership. There we go. Put those over there and make it look nice and pretty. All right, well, I don't like jaggy things, so like that. Oh, that's perfect. All right. That's what we're expecting, right? We're expecting a draft on your draft, right? And in your final, once you've actually implemented your database, this is what we're expecting here. Right? Any questions? Oh, by the way, you can save it as export it as a PNG or an SVG. Right? Anybody know what an SVG is? Scalable vector graphics. Right? That is the standard. Right? PNG is just like a static image with pixels and stuff, but SVG is like an actual language that specifies how stuff is done. So that if you've got this nice little curve here and you infinitely zoom in on it, it will stay a nice little curve instead of having a bunch of pixels and dots, right? Because it's a mathematical representation of that curve. PNG is fine. But then you get into like potato quality when you start zooming in on stuff, right? That's what it looks like. Right? All right, no questions? All right, well then have a good break, and I'll see you in a week or two.